Okay, welcome to Unit 1 Notes 4. Today we're going to be discussing the organization of data within the science community. How do we organize data? How do we make sure the data is good data versus bad data and taking measurements and things like that. So the PDF for this section of notes can be found right there. And this lecture is going to be right here, this link right here that says Notes 4 lecture. And then later on there will be a video for the Notes 4 practice problems right there. All right, so without further ado, let's go ahead and jump right into Notes 4, Organizing Data. So before we get into the actual content, we've got a couple of warm-up questions to kind of ponder and think about and then possibly share with the class. The first one is, have you ever tried to do something difficult but kept on making mistakes? Were the mistakes the same mistake or different ones? Try to think of an example and be ready to share with the class. And then the second question is, what type of graphs can you think of? What kind of graphs are there? Can we, as a class, name all of the graphs that exist? So go ahead, pause for a few minutes, think about it, and then be ready to share. All right, so hopefully you were able to share some of your reflections for those two warm-up questions. But now we're going to jump into the actual material for this lecture, which is, organizing data and figuring out what type of graph to use. So first, let's discuss the types of graphs and appropriate situations in which you would use each one of these graphs. The first graph that we see here on the slide is the line graph. And line graphs are pretty common, and they are used for data that changes because of a relationship. And 90% of the time, that relationship is going to be time. As time moves forward, there's going to be a difference in a certain variable, and that means that we can calculate and show the differences in that variable over time. So for a line graph, we have to remember that there is a dependent variable and an independent variable, and you're doing a comparison between those two. So one key thing to keep in mind here is that the dependent variable right here is going to always be on the y-axis, and the independent variable is always on the x-axis. And that actually makes sense because if you recall from a few sections of notes ago where we discussed the difference between dependent variable and independent variable, we kind of talked about like that little trick to figuring out, okay, which one is the independent variable and which one is the dependent variable. What depends on the other? So does the temperature depend on the time, or does the time depend on the temperature? Okay, so kind of compare those two different scenarios in your head, and one of them is going to clearly make sense and the other one is not. So for instance, does it make more sense that temperature of the day depends on what time of day it is? Sure, that can make sense. As the day moves on from the morning to afternoon, it could get warmer outside. But it doesn't make sense the other way around. You're not going to say, hey, what time is it, to someone, and they said, well, it's 21 degrees Celsius, so it must be 3 o'clock. That doesn't make sense. So you always want to make sure that you're always putting the dependent variable, figuring out which one that is first, and putting that on the y-axis, and then putting the independent variable on the x-axis. Another example of a line graph could be, your height as you grow from your birth to throughout your childhood and even into your teens to adulthood. Typically, your doctor has a record of your height throughout those physical visits that you've had every single year, and you can actually create a line graph showing your growth throughout time. Similarly, you can measure the height of a plant and check out different types of fertilizers or amount of water, whenever type of experiment you're doing it where you're comparing it between one thing and another, usually that thing being time, you're going to want to use a line graph. The next type of graph that we're going to discuss is called a bar graph, and a bar graph is used anytime data is counted during an experiment. So over here we have an example of a chart where it says classroom size as the title, and then we have the number of classrooms on the y-axis and the number of students on the x-axis. So let's say you go around De La Salle and you walk around all the classrooms and you count how many students are there per classroom. Okay, and so you've created a little tally here, and then for every single classroom that had 21 students, you add a tally for 20 students, and then you're basically keeping a count of how many students are there per classroom. So it's a very easy graph. And this is the only time you would want to use a bar graph is when you're counting things. Another example of a bar graph that you could have where you're counting things is, let's say you wanted to find the distribution of Skittles and their flavors, like what the flavors are inside of Skittles and how many of each there are, to see which one's the most common. And so let's say you rip open a bag of Skittles, you empty it out, and then you separate them by color: red, orange, yellow, green, and I think purple is the last one. And then you might find that they could be all evenly distributed for the most part, or maybe one flavor is heavily favored and one is certainly not favored. So that's an instance where a bar graph might be used. The next type of graph that we're going to take a look at is a pie graph or a circle graph. They go by different names. This is a type of graph where you wouldn't necessarily want to show an amount, but you would want to show a percentage of an amount. Okay, so a pie chart shows how a certain quantity is broken down into parts. And normally you're going to see a complete pie chart. Sometimes you might see like a Pac-Man style pie chart where they don't show you the whole thing, but normally they're going to show you the whole thing that equals 100%. So in this graph that we see here from way back in 2003, cheese production by type. So this is from the U.S. Department of Agriculture, probably showing all of the cheese that is being produced in the United States and what type of cheeses there are. So you can see here, based off of the percentages, 23% of all cheese is cheddar and 24.4% is mozzarella. Okay, great. I can add up all those percentages and they'll equal to 100, but it doesn't necessarily tell me how much cheese was being produced. Okay, so a graph like this, a pie chart, again, useful when you're trying to show parts of a whole and breaking down a whole into different segments to show how it's distributed over the entire sample. So now that we've discussed the different types of graphs that we're going to use and different scenarios in which we would want to use those graphs, we're going to move on to organizing data and knowing the difference between accuracy and precision. So in the science community, those terms are very important. You want to be accurate and you want to be precise. And a lot of times people confuse those two terms. So before we do that, we're going to actually watch a YouTube video. I'm going to plug into here and we're going to take a look at how accuracy and precision, although they sound similar, they are actually two different things.
As the story goes, the legendary marksman William Tell was forced into a cruel challenge by a corrupt lord. William's son was to be executed unless William could shoot an apple off his head. William succeeded, but let's imagine two variations on the tale. In the first variation, the Lord hires a bandit to steal William's trusty crossbow, so he is forced to borrow an inferior one from a peasant. However, the borrowed crossbow isn't adjusted perfectly, and William finds that his practice shots cluster in a tight spread beneath the bullseye. Fortunately, he has time to correct for it before it's too late. Variation 2. William begins to doubt his skills in the long hours before the challenge, and his hand develops a tremor. His practice shots still cluster around the apple, but in a random pattern. Occasionally, he hits the apple, but with the wobble, there is no guarantee of a bullseye. He must settle his nervous hand and restore the certainty in his aim to save his son. At the heart of these variations are two terms often used interchangeably: accuracy and precision. The distinction between the two is actually critical for many scientific endeavors. Accuracy involves how close you come to the correct result. Your accuracy improves with tools that are calibrated correctly and that you're well trained on. Precision, on the other hand, is how consistently you can get that result using the same method. Your precision improves with more finely incremented tools that require less estimation. The story of the stolen crossbow was one of precision without accuracy. William got the same wrong result each time he fired. The variation with the shaky hand was one of accuracy without precision. William's bolts clustered around the correct result, but without certainty of a bullseye for any given shot. You can probably get away with low accuracy or low precision in everyday tasks, but engineers and researchers often require accuracy on microscopic levels with a high certainty of being right every time. Factories and labs increase precision through better equipment and more detailed procedures. These improvements can be expensive, so managers must decide what the acceptable uncertainty for each project is. However, investments in precision can take us beyond what was previously possible, even as far as Mars. It may surprise you that NASA does not know exactly where their probes are going to touch down on another planet. Predicting where they will land requires extensive calculations, fed by measurements that don't always have a precise answer. How does the Martian atmosphere's density change at different elevations? What angle will the probe hit the atmosphere at? What will be the speed of the probe upon entry? Computer simulators run thousands of different landing scenarios, mixing and matching values for all of the variables. Weighing all the possibilities, the computer spits out the potential area of impact in the form of a landing ellipse. In 1976, the landing ellipse for the Mars Viking lander was 62 by 174 miles, nearly the area of New Jersey. With such a limitation, NASA had to ignore many interesting but risky landing areas. Since then, new information about the Martian atmosphere, improved spacecraft technology, and more powerful computer simulations have drastically reduced uncertainty. In 2012, the landing ellipse for the Curiosity lander was only 4 miles wide by 12 miles long, an area more than 200 times smaller than Viking's. This allowed NASA to target a specific spot in Gale Crater, a previously unlandable area of high scientific interest. While we ultimately strive for accuracy, precision reflects our certainty of reliably achieving it. With these two principles in mind, we can shoot for the stars and be confident of hitting them every time.
All right, so hopefully after that video, you've got a better understanding of accuracy versus precision. We're just going to do a quick review one more time and another example of how you could have accuracy without precision and precision without accuracy when you have both and when you have neither. All right, so just recapping, accuracy is how close your measurements are to the actual value. If you have a target in mind, you're going to want to reach that target, and when you try to reach for that target, how close you are is going to be described at how accurate you are. So in this example, this ring toss game that we see here, obviously you want to get this ring around this pole here, so if you can get that, you are being accurate. Okay, so in this example, we are actually accurate and precise. Over here, we're being accurate, but we're not really being precise because not all of our measurements are the same, or not all of our trials are the same. Every single time we threw the ring, it landed pretty close, but not quite there. All right, so that's the kind of difference between accuracy and precision. On the other hand, precision is basically how close your measurements are to one another. It doesn't actually mean that you are hitting your target, but it means that you are making consistent mistakes that are the same. Okay, and that's actually pretty easy to fix. It's much easier to fix poor accuracy and good precision than it is poor precision and good accuracy. All right, and I'll explain that a little bit next on the slide. There's a good picture. But over here in this picture on the left, we can see that all of the rings, they're hitting the same spot. And basically what that means is that you have good precision, but the accuracy just isn't there. And then finally in this last picture, all of the rings are just kind of tossed wherever. That's not really good accuracy or good precision. So that's the worst case scenario. Definitely if something's going on in a scientific experiment where none of your results are hitting the same target and they're just kind of all over the place, that's kind of a bad situation you don't want to find yourself in as a scientist. Here's another example, just again, target practice, similar to what we saw in the video. Just last time we're going to talk about accuracy and precision. In the top left, we've got low accuracy, low precision. Obviously, we're going to try to aim for the bullseye in the center, and whatever we're throwing there, whether it's like arrows or bullets or whatever, they are just not hitting the mark. That's low accuracy, low precision. In the top right, we have low accuracy, high precision, because all of the bullets or arrows or whatever we're throwing, they're kind of hitting the same spot, but it's not where we want it. All right. In the bottom left, we are kind of hitting the same region, which is the bullseye region, pretty close. So that's good accuracy, but not all of the bullets are hitting the exact same spot. So that's a low precision. And then finally in the bottom right, we have high accuracy, high precision. That means you're hitting your target and you're doing it every single time reliably, which is good. Before I mentioned that it's easier to fix accuracy than precision. So what I mean by that is If you have to compare these two scenarios, we have this scenario here, the low accuracy, high precision, and the high accuracy, low precision. Which one is kind of easier to fix? It depends mostly on your experiment and what you're doing, but let's say, for instance, you're working on a free throw shot in basketball, okay? And when you throw the basketball at the hoop, it doesn't go in, but you're hitting the exact same spot. So what that means is that you've got low accuracy, high precision. It's easier to make some fine-tune adjustments and fix that so that you can hit the target every single time than something like this where you're close, your technique is pretty good, I guess, but you're not doing it correctly every single time perfectly. So it's easier to fix low accuracy, high precision for the most part than high accuracy, low precision. So you've got a practice problem in your notes. I would like for you to reflect and possibly share in class. Which one do you think is more important, accuracy or precision, or are they equally important? And I'd like for you to kind of take a moment and just reflect on that, explain your answer, just come up with an example possibly. And that's actually the second question. Think of an example where you might see accuracy without precision or precision without accuracy, and then explain how that might affect the outcome. What would happen if your example had both? So come up with a couple of answers for this. Be prepared to share with the class, and then we'll come back in a minute. All right, hopefully you were able to take a moment and just kind of reflect on that and possibly share with others. But we're going to move on to our last and final topic in terms of organizing data in science, and that is significant figures, or as a lot of people call them, sig figs. Significant figures are basically ways for scientists to make sure that our data is reliable and that there's not a whole bunch of extra numbers around, because the precision of measurements can vary, and so scientists use significant figures to show the precision of a measured quantity. So they're going to show how precise their measurements can actually be. For instance, if you wanted to weigh an object in your hands, you could probably get close to the nearest pound if you're really good, probably not to the nearest ounce. For example, if I gave you, let's say, a water bottle filled with water and I told you to weigh it in your hands, and you said this weighs exactly 2.86429 pounds, I probably wouldn't believe you, just because there's no way you could tell me exactly how much that weighed, because that is a way too precise of a number. So we want to make sure that the numbers that we have in our data are going to be significant in terms of how precise they can be. All right? Significant figures are the numbers used in calculations that must be rounded to the least accurate measurement. So when we're doing science experiments or any type of calculations, we want to make sure that the significant figures are going to be the ones that are being represented, and we're leaving out all other numbers. All right, here's an example of a situation where we have significant figures. So let's say there's a guy who works in a lab and he just started, and his boss tells him, I need you to take a sample of liquid in this flask and I need you to divide it exactly into 7 parts. So there's 32.5 milliliters in this sample, and I need you to try your best to give me a number and tell me how much does each part have if we divide it into 7 equal parts. All right, so let's say you pull out your calculator on your phone and you simply do 32.5 divided by 7, and you take a look at it and you say, all right, boss, each sample is going to have 4.6428 milliliters. And so that's what the answer you give him, and the boss is going to say, nope, that doesn't sound right. Go back and do it again. So you might be confused. You did it on the calculator on your phone. How could that be wrong? So you go and find like an actual scientific calculator, okay? And when you do the math, it'll show you more numbers. So you do 32.5 divided by 7, and you get a few more numbers. So each one's now going to be 4.642857 each. All right, so a few more numbers. And so you think, okay, this is for sure, more numbers means more precision, more accuracy. I can go give that to my boss now. You give the boss your number, and he says, still wrong, go do it again. So now you go to an even better calculator. Let's say you borrow one from a colleague that has even more space for numbers, and you do the calculation again, last time, and now you have this really, really, really long number when you divide 32.5 by 7. All right, so you take that and you give that to your boss, and now he's just absolutely furious with you. because you're not understanding the point. And the point is, there is absolutely no way you can measure this level of precision. Okay? And what I mean by that is a milliliter is actually a really small amount of water. It's like if you took a plastic cap from one of those water bottles, the really, really skinny plastic caps, and you filled that with water, that's about a milliliter. And so if you wanted to divide that into tenths or hundredths or even in the thousandths place, there's no way you can measure that reliably and give it that much level of precision. Okay? So probably in this scenario, the boss was probably looking for a number that had fewer digits, probably 4.64, maybe even just 4.6 milliliters would have been close enough. So that's what it means to be significant. 4 is definitely significant because you can measure 4 milliliters. You could probably even measure zero point 0.6 milliliters, but there's no way you can measure 0.04 milliliters or 0.002 milliliters. And so all of these extra numbers that we have on the excess, they're not really needed. Okay, so that's what it means to be significant. All right. So, for example, we're going to take a look at this scale, this triple beam scale, and we kind of reviewed at one point to how to read this. And you're going to need to know how to do this when we do our lab in the future. And basically, what we're doing here is adding up all of the weights. So, take a moment here, look at the numbers on the scale, and try to give me the most precise answer that you could give me in terms of the scale and the measurement that is giving us. So pause for a moment here, and we're just going to take a look. All right, so hopefully you were able to come up with an answer as a class or maybe just in your heads. Obviously, we have at least 300, so that 3 in the front is significant. We have at least 70, and we have at least 3. So definitively, you could give me an answer that's 373. But could you give me an answer that's even more precise? Well, probably, because we have these little dash marks between the 3 and the 4. So we have 373.1, 2, and 3. Okay, so you could definitely tell me 373.3. And then if we kind of zoomed in and saw where the little point is, it's actually in between the 3 and the 4. So you could tell me 373.35. And so that's the answer that you should have gotten in terms of measuring. And that's the highest level of precision. You could not add any other numbers because there's no way you can tell, based off of the measurements that we are given, how any extra decimal places. So when we work with sig figs, there's actually a few rules that we need to be able to follow in order to determine whether or not the number is significant or not, or each digit is significant or not. All right, and there's 6 rules that we're going to go through, and then at the very end, I'm going to have like a condensed version where we can kind of condense it into 2 rules. All right, so the first rule that I'm going to talk about is rule number 1. Non-zero digits are always significant. If you're given a really long number that's a measurement, any number that is not 0, so that's 1 through 9, any digit that is not 0 is going to be significant. Okay, so for example, the number 26.38 has 4 digits, 2, 6, 3, and 8. All of these are not 0, meaning 26.38 has 4 sig figs. Each of these numbers is significant. Right? 7.91 has 3 numbers that are not 0, hence 3 sig figs. Okay, each one of these is a significant digit, and therefore it has 3 sig figs. Rule number 2: 0 is only significant if it meets at least one of these conditions. So here are the rules for 0. It is a trailing 0 and in the decimal place, or it is between 2 significant numbers. Okay, and so let's take a look at an example problem. 406. Following just rule number 1, 4 is not 0 and 6 is not 0, so we have at least 2 sig figs. But what about this 0? When is this 0 significant? Well, it looks like this 0 meets this rule right here. It is between 2 significant numbers. So 406, this 0 is sandwiched between this sig fig, 4, and this sig fig, 6. So if it's sandwiched in between, it counts. So this number 406 has 3 sig figs. The number 26,001, so it's just a bigger sandwich. 2 is significant, 6 is significant, and 1 is significant. And these zeros, they're sandwiched in between them. Therefore, they have to count. 26,001 has 5 significant figures. All right, rule number 3. A final zero or a trailing zero only in the decimal portion are significant. Okay, so what does that mean? If I'm given the number 0.05, okay, it has to be a trailing zero in the decimal. Well, this zero, it's not sandwiched like before, and it's not in the decimal portion, so it is not significant. This zero, it is in the decimal portion, but it's not trailing. And what do I mean by trailing? It means that over here, they're trailing at the very end of the number. However, this 5 is a non-zero number and automatically counts, hence we have 1 sig fig here. Okay, but if we compare 0.05 to 0.0500, well, these two zeros still don't count. This one, however, is in the decimal portion and it is trailing, and so is this one. So these are significant. Okay, and this is where it can get kind of confusing because mathematically, those two numbers are exactly the same. If you plugged both of those in a calculator, they'd be exactly the same. However, those two measurements are different because this one, the 0.05, it could have been rounded. It could have gotten, it could have been 0.052 and then you round it down to 0.05, or it could have been rounded up. 0.048 could have been rounded up to 0.05. But over here, you're showing me a level of precision that no, it is exactly 0.0500. That is a more precise number. It's a more precise measurement. All right, what about this one, 0.03040? This one's a little bit confusing, but let's take a look at it. 0 in the front does not count. It's not sandwiched. It's not in the decimal portion. This one is in the decimal portion, but it is not trailing. This 3 automatically counts. This 4 automatically counts, and the 0 in between is sandwiched. Therefore, it also counts. And then this 0 also counts because it is trailing in the decimal. So this has 4 sig figs, this 3, this 0, this 4, and this 0. All right. Now, what about numbers in scientific notation? This is where we can get a little bit tricky. So in scientific notation, we completely ignore the part in scientific notation here, this 10 to the 12th. Don't even think about it in regards to sig figs. Only look at the mantissa right here, the 2.3. The 2.3 is 2 non-zero numbers. We have 2 non-zero numbers, hence we have 2 sig figs. But taking a look at 2.30, 2 is not 0, 3 is not 0, and then this 0 is trailing in the decimal, so that counts as well. 3 sig figs here. All right. Rule number 4. Space holding zeros on numbers less than 1 do not count. So what do I mean by that? Taking a look at those numbers we just saw before, that's a space holder. That's the number that we call a space holder, hence why this has only 1 sig fig. And this is a space holder. That's the same 0. Okay. This number right here has a space holder, and then these two are not space holders. This is just a space holder. The number in front as well is a space holder. Okay. Rule number 5, on numbers less than 1, remember to always place the 0 in front of the decimal. Okay, that's just a simple rule. In math calculations, in science, we always want to put a 0 in front. Never put like 0.05. I know mathematically this looks the same, but it's just a good habit in math. We always want to show that 0 in front if the number is less than 1. All right. And then the final rule is that trailing zeros and whole numbers do not count unless there is a decimal. So just a final review. 200, they're trailing, but they're not in the decimal. So the only significant figure here is 2. The only sig fig is there. But 200.0 has 4 sig figs, and this is why. Even though these two zeros are not in the decimal portion, they are sandwiched between this 2, which is significant, and this 0, which is also significant. Why is this 0 significant? It is because it is trailing in the decimal portion. So if this one is significant, this one's significant, everything else in between has to be as well. All right, 2.0, trailing in the decimal, looks good, so that's significant. And 2.00, these are also significant, trailing in the decimal. All right, so below your notes on the very bottom of the sheet, if you want to simplify those two rules to these basic bullet points right here, you can. This is not in your notes anywhere, but if you want to jot this down for a moment in your notes, you can pause the video right here. I've taken those 6 rules and kind of condensed them into these 2 points right here. And so you can take a look at this and kind of apply this to every number, and it should work for the most part. So the first bullet point says numbers that are not 0 always count. And the second point is, when do zeros actually count? Zeros only count if they meet one of the following criteria. They don't have to meet both, just one. They are sandwiched between 2 sig figs, or they are trailing in the decimal. So those are the 2 scenarios in which a 0 will count. So go ahead, take a moment if you need to write that down in your notes, and we will continue on with some sig fig problems. Alright, so hopefully following those 2 rules for sig figs, or if you want to take a look at the 6 rules ahead of it that we covered before, you can kind of identify how many sig figs each number has and then use them for calculations, which is what we're going to actually practice right now. So let's take a look at the sig fig rules for addition and subtraction. There are a set of rules for adding numbers or subtracting numbers for sig figs. So the rule is that for addition and subtraction, you want to look at the decimal portion of the numbers only. Okay, so you're only looking at the decimal portion. And here's what you do. Step 1, count the number of sig figs in the decimal portion of each number in the problem. Okay. Step 2, you're going to add or subtract the numbers just like the normal fashion. You could even plug it into your calculator if you want. And step 3 is you're going to round the answer to the least number of places in the decimal portion of any number in the problem. Okay? And I'm going to give you an example of that with this right here. So let's say we have these 3 numbers: 48.675, 9.32, and 1103.000. Okay? So we're adding those 3 numbers. If I were to put them into a calculator, I would get 1160.995. Alright, so just reviewing these rules. Rule number 1 is count the number of sig figs in the decimal portion only. We've already added, and now we're going to round our answer. Okay? So 48.675 has 3 sig figs in the decimal portion. Let me get rid of that arrow. Right here, 675. We're only looking at the decimal portion. That's 3 sig figs. 9.32 in the decimal portion. That's 2 sig figs. And then these zeros right here, they're trailing and they are in the decimal, so they do count as sig figs. So which one has the fewest amount of sig figs? Well, it's this one right here, 0.32. The fewest amount of sig figs in the decimal portion. This one only has 2. The number above it has 3, and the number below it also has 3. Okay? That means the answer, which currently has 3 numbers in the sig figs, can only have 2. And the reason for that is because we can't give that level of precision anymore based off of that second number. Okay? So the new answer must have 2 sig figs after the decimal. All right, so what do? We've got maybe a couple of guesses what we could do. Do we just cut off that 5 at the end entirely and just ignore it? Or is there some rounding that's being involved here? Well, the correct answer would be 1161.00. And the reason for that is because we had to round that 5 up. We had to round this 9 up because of this 5. So we were getting rid of this 5 for sure, but that means we have to round this number up, this 9, which turned that into a 10. So we leave the 0 and carry over the 1, and that changed this 9 into a 10. Leave the 0 and carry over the 1, and now we're left with 1161.00, making sure that our answer has 2 sig figs in the decimal portion because this number had 2 sig figs in the answer portion. Okay? Subtraction works the exact same way, except for adding, you're doing subtracting. You're doing the exact same rules in terms of applying the correct sig figs to the final answer. All right? Now, when it comes to multiplication and division, it's pretty similar to addition and subtraction. But here are the rules that apply for multiplication and division. The least number of significant figures in any number of the problem determines the number of significant figures in the answer. This means you must know how to recognize significant figures in order to use this rule. So for multiplication and division, instead of looking just at the decimal portion, you're actually looking at the whole number. Okay? So for instance, we've got 30.0 and 4.0. 30.0 has 3 sig figs. Every single number there is significant. This 3 because it's not 0. This 0 because it's trailing and in the decimal. And then this 0 is sandwiched between them. So all 3 are significant. Over here, I've got 4, which is not 0, and this is 0, which is trailing in the decimal portion. So these are significant as well. 3 sig figs and 2 sig figs. Which one's the lowest number? This one. Fewest amount of sig figs is 2, which means my answer can only have 2 sig figs total. Not in the decimal portion, just total. For multiplication and division, you're looking at the whole number. Okay, so the new answer must have 2 sig figs. How would you report this number as 2 sig figs? Well, it's actually not too complicated. You would report it as 120. Is this 1 significant? Yes. Is this 2 significant? Yes. Is this 0 significant? No, it is not. It is not sandwiched. It is not trailing in the decimal, so it is not significant. Okay? One more practice problem here. We got 15 and 4.0. So 15 is our top number. That's obviously 2 sig figs. And 4.0 has 2 sig figs as well. So we've got two numbers that both have 2 sig figs. That means my answer has to have 2 sig figs. And this is a kind of a tricky one because if we did 60, 60 only has 1 sig fig, right? So our answer has to have 2 sig figs, but 60 on its own only has 1. So if we put 60.0, that would actually be 3 sig figs. So we don't want 3 and we don't want 1. So how would we report this as 2 sig figs? Would we either round down or round up to 59 or 61? Well, no, because that's not correct. We would actually go back and use scientific notation. So this is kind of where scientific notation comes into play and why it's so important. 6.0 times 10 to the first is the correct way to write this calculation. It may seem silly, but this is the correct way we do it in science. 6.0 has 2 sig figs, and so that's how we would write this answer. So let's take a look at this example where we can actually do a density calculation. Let's say you wanted to take the density of pennies to determine, what their density is. You took a whole bunch of pennies and you put them on a scale and you found their mass to be 31.155 grams. Let's say your scale that you were using was really precise. It was a really good scale and it could give you that level of precision, 31.155 grams exactly. However, the volume was not as precise. You could only get it to 2 sig figs, 3.5. So the way you were measuring your volume, not as precise as the way you were measuring your mass. So you only got 2 sig figs out of that instead of the 5 you got from the mass. Now when you're doing a density calculation, it's density is equal mass divided by volume. Okay, so you're doing a division problem. This mass divided by this volume will give you an answer. Okay, if you did this in a calculator, you'd get 8.9014285171, right? But your answer has to have the fewest amount of sig figs from the problem. So you had 5 and you had 2. 2 is a smaller number, therefore your answer can only have 2. So you could only give an answer of 8.9 grams per milliliter, right? So that's how you would do a calculation for sig figs. Hopefully it's not too complicated. There's a couple of practice problems that we're going to take a look at, and there's going to be a video on that in Canvas as well.